Okay, let's go ahead and start the class. We are going to finish chapter 8 today. We are going to continue the discussion we have had. We will have a very small, a small recap on whatever we discussed in the previous lecture, just to make sure we are all up to speed. And then we will continue the discussion. We will finish the chapter 8 discussion. And that will be it for today. Again, keep in mind that your exam is next Thursday. Exam 2 is going to be next Thursday. Let me actually write it on the board. So exam 2, April 15, next Thursday. It will be 75 minutes. We will solve some example problems. We will have an exam review from chapters 4, 5, and 7 that are included in this exam on Tuesday. And after the exam, we will do the chapter 6, then we will come back to chapter 8, solve some example problems, and we will do a review on this. We will go for the final exam. Is there any questions about the exam? Okay. There's also something else that I needed to mention. Your evaluation, your course evaluations are going to be open from April 13th, so Tuesday. You will receive an email as well. Whoever fill out the evaluation and send the receipt to me, you will receive an email receipt, right? Whoever sends me the receipt, meaning that whoever tells me that they have filled out the evaluation, will get a bonus point, 2 bonus points. So 1% of your total grade can be just 1% of the final grade Just send me the receipt. Make sure you only send me the receipt. You shouldn't like take a screenshot of your evaluation and send it to me. The evaluations are supposed to be anonymous, right? The receipt only says that you have filled out the evaluation for this course. That's it. Just forward that email to me or take a screenshot or whatever of that email, send it to me. You will get the evaluation. I would rather you wait until the last lecture to fill out the evaluation. What we will probably do is to give you 15 minutes at the end of the last lecture. All of you have laptops, and you can actually put it on your phone as well to fill out the evaluation. Mainly because you will have a better idea about the whole course. I definitely appreciate comments on what parts of the class you liked, what parts of the class you didn't like, and what you think I should do to improve the experience for students, right? The learning and all of those things. So is there any questions about this? Okay, it's pretty straightforward. And your homework is due Tuesday. Don't forget your homework. You have to submit your homeworks. And I guess that's it. Let's do a recap on whatever we did on in the previous lecture. The idea was we talked about viscous flow inside the pipes. And to start the recap, as I said, every day we are going to have an attendance quiz. So let's start with the attendance quiz, and we'll go from there. The attendance quiz is this. What is the main difference between laminar and turbulent flow inside the pipe, or in general. And what is the value, or what are the values for of Reynolds number for the laminar flow and turbulent flow inside the pipe? This is your attendance quiz. You will have 5 minutes to give me some answers. We have already discussed this, so you should have it in your notes if you took any notes in the previous lecture. And whoever give me the correct answer will get bonus point. But if you don't have the correct answer, make sure to submit your answers anyway to get the attendance grade. Can you repeat that? Sure, yeah, definitely. Yeah, what I'm going to do from the next lecture is to bring the extra sheets of paper for you, so you don't have to tear something out of your notebooks. Sorry about that. Okay, so I guess everyone's ready to submit their answers. You can just pass it on to your friends. And you can give that to me. Thank you. Thank you. Thank you. Thanks. Okay. So, as you probably have mentioned in your answers, laminar flow is ordered, right? But in turbulent flow, flow is we will have a lot of mixing, swirling motion, and we have a lot of vortices, all of those things, all of those fun things. So inside the pipe, your laminar flow will look like this, right? But turbulent flow will be a little unorderly, something like this, right? Will be fluctuating. We could also say that your V at a point with respect to X or T for laminar flow will look like this. For turbulent flow, it will look like this. The value of Reynolds number, though, is a little approximate. Your book says that laminar flow is for the cases where Reynolds number is smaller than 2100. In a lot of other books, and this is the other value you're going to see in your heat transfer course, is that they use a value of 2300, right? But doesn't matter which value you choose as long as you are consistent, right? And turbulent flow starts at the value of 4000. Okay, we talked about the laminar flow in detail in the previous lecture. We talked about actually some of the relationships that apply to both laminar flow and turbulent flow. But we want to discuss the turbulent flow in more detail here. But the problem was, if you recall that this was the last thing we talked about in the previous lecture, is these fluctuations. When you have fluctuations, when your flow is unsteady, it is going to be very hard to come up with a closed form analytical solution for your problem, right? So what do? We divide the velocity profile to an average or mean velocity, mean or average velocity, plus the fluctuations, u prime. If you do so, you can actually show that your mean velocity is going to behave like laminar flow. And when you add the fluctuations on top of it, you will get the velocity profile. And for most of the for most of the analysis, we can actually use the mean velocity, which can be treated as a steady case in which the velocity doesn't change, for the analysis inside pipes and all of those things. So we don't need to care about fluctuations that much. We can do a lot of calculations, all of the analysis with a good degree of accuracy using only the mean velocity of the turbulent flow. Okay? The only, and you will see where we need to include the effects of turbulence here. So if we only use the mean velocity for your laminar flow, the idea was your velocity profile inside the pipe looks like this, right? We had a maximum velocity, U max. I don't know if I mentioned this, but I'm mentioning right now. And we also have an average velocity, which is always half of U max. This is true for laminar flow. Okay. Well, what's going to happen for the turbulent flow is that if you only plot the mean velocity, it will look more something like this. You still have your U max, but your U average is going to be different for different cases, for different pipes, for different fluid, but it's usually around 80% or 0.8 of U max for your turbulent case. Okay. The goal in this type of analysis, if you recall, was to find either the pressure loss or the velocity profile or the diameter of the pipe needed to maintain that pressure loss or that velocity profile. That was the goal. And we were able to find the pressure loss and the velocity profile using the conservation of mass equation and conservation of mass and the momentum equation. Momentum equation gave us the pressure loss, right? Or the force balance. It's the same thing. Okay. What did we do with the conservation of mass? It's just a recap. For the conservation of mass, we just said, because this is something you will see on Tuesday as well. Whatever goes in is going to come out, right? The idea here inside the pipe, this is the type of velocity profile we are dealing with, right? If you recall from chapter 5, we said we can use U average to replace with the non-uniform velocity, to use U average instead of the non-uniform velocity and use this equation. Rho UA is going to equal to rho U average A1, A2. This was true, let's say this is section 1. This was true for the laminar flow, right? And these will cancel out. So your U average for laminar flow, or a mean velocity, whatever you want to call it, is going to be equal for laminar flow. But we can do the same analysis for the turbulent flow as well, with the mean velocity of the turbulent flow, U bar. So for turbulent flow, again, m.1 is equal to m.2, conservation of mass, right? And these parts are only walls. So there is no mass going out in any of the other direction. Mass is coming in here, going out here. Okay? m.1 is equal to m.2. That's rho 1. U bar average, which was the 80% of the maximum velocity in most cases. A1 is equal to rho 2. U2 average. A2. These will cancel out. And again, the velocities are going to remain constant. What does this mean? This means that for a fully developed turbulent regime, turbulent flow inside the pipe, fully developed turbulent flow, mean velocity, and that's only mean velocity, right, is going to remain constant. Mean velocity, U bar. Fluctuations are going to change, right? But mean velocity is going to remain constant. You may ask, what was the fully developed flow? This is also something we discussed in the previous lecture. Just as a reminder to refresh your memory, the idea was in a pipe, when you have flow coming in, because of the presence of the wall and a condition we call no slip condition, the velocity at the wall is going to be 0. That's why we are going to get body layers in which the velocity goes from 0 to U infinity, whatever that is, right? This is something we discussed in the previous lecture. And wherever these boundary layers merge, we are going to have, this is the entrance length, right? Length. And afterwards, we are going to get a fully developed flow. This fully developed flow, it can be laminar or can be turbulent. And your velocity is going to remain constant inside this pipe. Okay, so this was the conservation of mass. As you can see, we get the same conclusion as we did for the laminar flow, for the turbulent flow, as long as you are dealing with the mean velocity. Okay? And for the forces, we're going to have the same conclusion. Again, to refresh your memory, pressure loss was related to the wall shear stress for tau of W, that's shear stress at the wall, L divided by D, right? Again, these are true for both conditions, both turbulent and laminar flow. One other thing that we didn't have the time to do was to apply the energy balance, energy equation, right? Energy balance here in general is going to be like pressure between 0.1 and 0.2. We have the pressure head plus the velocity head. We didn't talk about this alpha correction factor, so because we skipped chapter 6, but just accept it from me. And then P2 divided by rho g, alpha 2 plus HF. Who remembers this type of energy equation? We talked about it in chapter 3. This was the pressure head, right? This was the velocity head. This is essentially a variation of Bernoulli's. This was the elevation head. Do we remember this? Yeah? Does it look familiar? Okay, that's good. There's one additional term here, and that's called H of L, or head loss. Okay? Velocity does not change here. That's something we just proved. So they can cancel out. Elevation also does not change. That will cancel out as well. So if you just rearrange things, rho g H of L is going to be equal to, so we can calculate the head loss using the pressure drop or pressure loss, right? And this head loss is a more common variable in the design world in general. Is there any questions here? Okay. So we have the head loss, we have calculated the pressure loss. These are the things we did in the previous lecture as well. And we can actually relate this pressure drop, this head loss, to the wall shear stress as well, as your head loss is going to be equal to 4 multiplied by your shear stress at the wall divided by the diameter of the pipe. Or actually, let's do rho g here. Length of the pipe divided by the diameter of the pipe. Then the next step, or the next question we had to answer here, was how to calculate the wall shear stress, right? Other than that, the length and diameter, rho and g are all design parameters. Like we are the ones who design L, D, all of those things, and rho and g are water, oil, whatever that is, right? And gravitational, as long as you are living on Earth, you are going to use the gravitational acceleration of Earth. So how can we find the wall shear stress? To find the wall shear stress, we went back to chapter 7, dimensional analysis, right? And we actually defined this friction factor, F. Right? This was the thing we used, or Darcy. I forgot to mention the inventor's name. This guy was Darcy. Darcy friction factor. We defined Darcy friction factor as F equals to 8 wall shear stress divided by rho v squared. And we said it is a function of Reynolds number, rho vd divided by mu, diameter of the pipe. But something that we didn't mention for the laminar flow was the other parameter that is going to be important when it comes to calculation of this wall shear stress, and that is the surface roughness, surface of the pipe. So laminar flow, as long as you have the Reynolds number, if you recall, we introduced this equation that your Darcy friction factor is equal to 64 divided by Reynolds number, right? This is something we introduced. We said, as long as you can calculate the Reynolds number, you should be able to calculate the friction factor, and you plug it in here. In this equation, you find the shear stress, then you find the head loss, and you can find the pressure drop as well. But when you're dealing with turbulent flow, surface roughness, or epsilon, or its ratio with diameter. So surface roughness divided by the diameter of the pipe is also very important as well. So what does this mean? This essentially means that your friction factor is a function of Reynolds number and surface roughness. So we cannot have an equation as simple as this, right? We have to include the surface roughness in this calculation somehow. Well, before moving on, I have one question for you. Do we understand what surface roughness is? Have you ever heard about surface roughness? No? Okay. You have never heard about it in solids, or? Okay. Surface roughness. Surfaces. In this course, we only give you one value for it. So in an exam, I will tell you surface roughness is this, right? 0.6, 0.1. But surface roughness is the degree of roughness of the surface, right? Of the surface of the pipe. Okay. What does it mean? Like a smooth surface is just a very smooth line, right? As you go to rougher surfaces, your surface will start to look more like this. Okay. So a smooth surface, a rough surface. Like an example of a rough surface is the or let me give you an example of a smooth surface. An example of a smooth surface is sanded steel, right? When you put your hand on it, it's very smooth, right? It's literally, that's what it means. Its surface is very smooth, right? But an example of let's see if you can think of an example of a rough surface. I guess wood, this untreated wood, is a very good example of a rough surface. You have a lot of holes, you have a lot of these type of fluctuations in the surface that are very important. Like the surface of a composite can become a composite can be. It depends on your how you have cured your composite, but that can be very rough as well. Or the surface of the I forgot the name. There are millions of examples of a rough surface. I'm pretty sure you have seen rough surfaces. So do we understand why this? It has a very literal meaning. How rough your surface is, right? How smooth the surface is, and this value of epsilon goes between 0 and 1, right? 0. A complete, smooth surface, 1, the roughest surface you can get. And the reason they are very important, especially in the turbulent flow, is that this will induce vortices. Okay. So these roughnesses will induce swirling motion. And swirling motion, I guess you haven't talked about vortices as well. A vortex, if you don't know, because I think you have never talked about this. A vortex, then what we call a vortex is a part of the fluid that is rotating around the center. So essentially, it has a swirling motion. And that patch of the fluid itself can move to location. So it is moving around itself, but it can move forward as well, right? Go. OK, so yeah, and these things are very important in turbulent flows. Yeah, if you ended up going to graduate school, here, there is a course called Viscous and Turbulent Flow. Over there, they will talk about this type of turbulent vortices, all of those things a little more. OK, so we already know about the friction factor. This is the equation for friction factor. We already know how to calculate the Reynolds number, right? And we already know how to calculate the we already know how to calculate the friction factor from here and Reynolds number from here. You can find the wall shear from here, this equation, and then find the head loss and the pressure drop. But we can combine all of those equations into this bigger equation for head loss that relates it directly to the friction factor. So you won't need to calculate the wall shear. FL divided by D, VS squared divided by 2G. Let's plug in the numbers. You will see this. OK. But how can we calculate the friction factor? We already know how to calculate the friction factor for laminar flow. How can we calculate it for the turbulent flow? There are a couple of methods. The most famous one is called the Moody Chart. And we will see the Moody Chart in a second. But before the Moody Chart, I want to give you an equation. It's called the Colebrook equation that relates your friction factor, Darcy friction factor, to Reynolds number and to Reynolds number and surface roughness. So it is 1 over a square root of friction factor equals to -2 log of epsilon divided by d, surface roughness divided by d, divided by 3.7 plus 2.5 Reynolds number multiplied by the square root of F. Okay. This is an empirical equation. Empirical. What does an empirical equation mean? Do we know what an yes? 3.7. 3.7. What does an empirical equation mean? No idea. There are many variables here, right? Reynolds number, surface roughness, friction factor itself, right? And the difference, yeah. They can actually change. Okay. So the main difference between an empirical equation and a regular equation, if you will, is that this empirical equation is not derived from any principles. It's just a curve fit. So there are a couple of people who ran some experiments and then gathered the data, fitted a curve to their data, and came up with this equation. So it doesn't matter what principle you use, you won't be able to find this equation because it's just a curve fit. We know what a curve fit is, right? Yes? OK. So that's the definition of an empirical equation. What does this mean? This essentially means that this empirical equation doesn't necessarily work everywhere, right? So you cannot just use this empirical equation everywhere. It has a very narrow scope. So this is something you can use to get a good idea of the Darcy friction factor. But to be able to have a better approximation of the Darcy friction factor, you want to use the Moody chart. And we're going to see the Moody. Wow. What's this? So we have to wait for it to. You want to use a Moody chart. Yeah, I mean, I guess in an exam, I won't even ask you to use this Colebrook equation because, as you can see from this equation, we have a square root of friction factor here and also inside this equation. So this is not a very simple equation to solve. You have to do a lot of trial and errors to be able to find the friction factor from this. But the only thing that you may need to do in an exam is to use, again, the Moody chart. Moody chart is one of the most famous charts in fluid mechanics, right? It gives you the friction factor as a function of Reynolds number, okay? So this part is only for the laminar part, as you can see. See, F friction factor was equal to 64 divided by Reynolds number. So we expected a linear curve, a linear, whatever you want to call it, a line, right? So for a laminar flow, this is where you find the friction factor. But as you increase the Reynolds number, we will have a transitional flow part, right, in which you may get two values for friction factor. Why is that the case? Because at some parts of the transitional flow, we have the laminar. We are still in the laminar flow regime. But at some parts of it, we are in the turbulent flow regime. So we usually don't deal with the transitional flow because it's too complex, too complicated. And you move on to the turbulent flow region. You may ask, why do we have this many lines for the turbulent flow region? And the reason is, in the turbulent flow, your friction factor is also a function of is also a function of surface roughness, right? So for different surface roughnesses, you're going to have different lines. Okay? And at some point, if you increase the surface roughness, the friction factor dependence on surface roughness becomes so much that compared to the Reynolds number, it will be just a straight line. So you will get a single value of friction factor for all of the Reynolds number because it's mostly dependent on surface roughness, not the Reynolds number anymore. Okay. Is there any questions so far? There are a couple of more things that we need to discuss, and then we'll be done with this chapter. So we are going to divide the head loss, H of L, into two different head losses. The first one we are going to call the major head loss, which is the head loss we have talked about so far. Right? H of L. This is something we talked about. We talked a lot about, and that will be that can be calculated as F multiplied by L divided by D, V squared divided by 2G, right? But there is also another type of loss that is called the minor loss. Minor loss comes into play when you have an elbow, for example, in your pipe. Or you have a valve. Or you have a two different sections that is fitted by a connection. Let's call it a fitting connection. These are going to cause some pressure drop in your system, but they are not going to be major pressure drops. And this is something we have seen previously, right? If you recall, we had this condition that flow would come in and go into the pipe. And we said how this is manufactured, this part of it is manufactured, is going to change the velocity inside here, right? That was the same idea. And if you don't remember it, that's all right. We will talk about this. So how can we calculate the head minor loss? Let's call it HL minor. Okay. It will be a minor loss factor, K of L, multiplied by V squared over 2G. So we're going to have a head loss factor multiplied by V squared over 2G. What if you have a system of pipes? What if you have let's say this type of system? This is a pipe, and then you have a fitting here, another pipe, you have another fitting, another pipe, you have a valve, and so on and so forth. How can we calculate the total head loss between this point and this point? It is actually very simple to analyze. You have to calculate this loss first, the major loss first, and then you calculate the minor loss of the fitting. Then you calculate the major loss here, minor loss of the fitting, major loss here, minor loss of the valve, and major loss here, and just add them up. Okay? So for the system of the pipe, your total head loss is going to be equal to sigma of all major losses plus sigma of all minor losses, right? Summation of all of those losses. Let's see some examples of this minor loss coefficients, K. Okay, this part, this first row here is something we saw, I think, in chapter 2. I'm not very sure though. So in chapter 2, if you have this type of, like, if you have a smaller pipe that is connected to a larger pipe, and you have this type of pipe inlet, your K of L is going to be 0.8. So if it had to calculate the minor loss here, you put 0.8 here, then you have V squared divided by 2G. Okay? And that's the V squared of this smaller pipe in this specific case. Right? In this one, you have K of L is 0.5, and this one, K of L is 0.03. Okay? And as your minor loss decreases, this essentially means that a special valve or fitting or elbow is not causing any pressure drop. It's causing less pressure drop, right? Because a smaller minor loss is getting closer to 0. So for this third case here, we are seeing the lowest minor loss, right? Because your K of L is 0.03. Does this make sense? And we can have K of L for pipe exits as well, and so on, and so forth. I mean, there are like specific examples that you need to do some calculations for K of L. But in general, I will give you the values for K of L that you need to have. Some more examples of it. Like you can see the elbows, K of L here is 0.3. For a flange case, a threaded case, K of L is going to be 0.9. This type of U-shaped pipe, K of L is 0.2, and so on and so forth. Different examples of it. Is there any questions about this? I can't hear. Let it go off. I can't. I'm sorry. This is like, yeah, definitely, yeah, most definitely. But I'm not sure about your homework because I haven't designed it yet. But in the exam, I will give you this KL. If it wasn't given, that's my mistake. You have to make sure to ask, right? Oh, this reminds me that I keep forgetting about this. One of the questions on exam 1 was actually, and I didn't know this until a week ago, and I was going back to the exam 1 and reviewing it for myself, was from chapter 4. That's the question that you had to talk about dynamic pressure, static pressure, and all of those things, right? It wasn't from chapter 1 to 3. So I will add, it either has 5 points or 10 points. I will add that 5 or 10 points to everyone, regardless of their answer. If you have answered it correctly, I will add 5.2. And before moving on, this is also something that I wanted to talk about as well. Let's actually finish the discussion, then we'll come back to this. But remind me that I wanted to talk about something about your grades. The last thing we want to talk about, not that much. The last thing we want to talk about is the special type of systems of pipes, or pipe network of pipes, what we call network of pipes. Okay, so let's say you are dealing with this network of pipes. Network of pipes. We can have two main different network of pipes. The first one is when your pipe is divided into two sections, two separate sections. So we essentially have two pipes here, and these one pipe here that is divided into two pipes, and then goes back to the first pipe. And the other type of network is when your pipe diameter is changing. Okay. What is the difference between these two, and what are the similarities? Okay. Again, whenever we are talking about a network of pipes, we are talking about the pressure loss or the head loss and the velocity or the volume flow rate. Let's actually talk about volume flow rate, V dot. Pressure loss, volume flow rate. Okay. This is analogous to electric potential and electric current. For these type of cases, between 0.1 and 0.2, your delta P is going to be constant. Your pressure loss is going to be constant. Okay? But your volume flow rate is going to be divided between the two pipes. If the radius is the same, you will have your volume flow rate will be divided by 2, right? Half of your fluid volume will go to the first pipe. The other half will go to the second one. So it is weighted by the radius of the pipe, right? But in this case, in the second case, your volume flow rate or velocity, or the mass flux, let's say mass, yeah, is the one that remains constant. And your pressure loss inside this pipe is going to be different than the pressure loss inside this pipe. Okay. So your head loss here, let's call this pipe 1, pipe 2, HL and 1 is equals to HL and 2. You can write the equations and set the equation. This is the type of equations you may get. I may tell you that the velocity here is this. You have the friction factors, all of the parameters I will give you, and ask you to find the velocity in the other pipe, right? What you need to do is to set these losses equal to each other and say the friction factor of the one multiplied by the length of the one, the first one, divided by the diameter, V2 2G is equals to F2 L2 divided by D2 V2 divided by 2G. Okay, so I may ask you to find the friction factor of the second one, right, and give you the velocity of the second one, right? I may ask you this. The idea is here. This is the equation you need to apply here. Okay, and we will solve an example from this later on in a couple of weeks. Is there any questions? We actually moved very quickly in this lecture. So that's all of the material we wanted to cover in this lecture. The thing that I want to mention is about your grades is that there are a couple of people who did very well on their exam 1, okay? And I thought to myself that it may be a little unfair to those who did well to not to extend the opportunity of dropping one of the exams to them, right? So if you have done well on your exam 1, if you have done well on your exam 1, what you can do is to use the exam 1's grade for those questions on the final exam that are from chapters 1 through 3. Does this make sense? So let's say you have gotten an A on exam 1. With the 20 points, you have received 100, whatever, right? And final exam is basically chapter 1 through 3, chapter 6 and 8, right? That was the idea here. I'm going to give you like 5 questions. You can just tell me that I want to use my exam 1 grade for the questions from 1 to 3, whatever question that is from chapter 1 to 3, right? If you haven't done well, I can use the grades of that part of the final exam for your exam 1 grade, and we're going to apply it to the, we're going to essentially use the reverse logic here as well. So if you have done well on the final exam, you don't need to answer those questions from chapters 1. Does this make sense? Okay. Yeah. Just, I guess, to make it easier for people who were able to do well on the exam 1. Again, your I mean, we are done with the lecture. So if you don't have any questions, we are done very early, much earlier than I anticipated. But if you don't have any specific questions, yes. 2g, yep. This is the velocity head, right? The part of the velocity. I don't hear you here. When are we doing next Tuesday? For which test? The final or the exam 2? Next Tuesday. Yeah. So next Tuesday, your homework is due. Make sure to work on the homework. The solution is going to be posted immediately after the due date. So if you have a question, you have to make sure to ask during the lecture. If there is one part or some parts of chapters 4, 5, and 7 that you feel like you didn't understand well, or you want me to focus on a little more, send me an email, okay? Let me know. Guys, and I will try to, so for that first exam, what I did, I solved complicated problems for you, right? Just because my idea was that if you can solve these complicated problems, you will be able to solve easier problems on the exam easily. But that confused you. I understand that. I shouldn't have done this. So we are going to try to be, and we will definitely be closer to the exam. So whatever you see in the on Tuesday, whatever example we solve on Tuesday, something similar to it will show up on the exam. Okay, does this make sense? Okay, so as long as you understand those parts, you should be able to do well. Yes.
So Tuesday for the practice problems, are you going to post the PDF of those?
That's right. So I will also bring in a copy of those problems to the class. So, yeah. Okay. Any other questions? Okay. Have a good day.